it's going to get you to some approximation. Now, to make clear, why is it that sometimes you get to this sense of approximation? So here in question 3, we are looking at applying the greedy algorithm to a tree. And in this case, you are at first given a tree here, and the tree has some numbers that are attached to the node. And we would like to find a path from the root to a leaf such that the total sum of numbers that are added up, they are all going to get to the maximum possible value. So here, let's say we are given this tree. So there is a brute force way of looking at every possible leaf, right? Because for every possible leaf, there is a specific pathway that will lead me to the root, and I can just sum up the values. So that's one way of doing it, but there will be a brute force way, and it's going to take us as many possibilities as there are leaf nodes. Now, there is a way to do this in a much simpler way, which is to simply look at one branch at a time. Now, so suppose that for question 3 here, given the tree that we have, we always need to start at the root. So the greedy algorithm will start at the root, and then each time we're going to make a decision. Do we go to the left or do we go to the right? And the decision is made based on the value that we see in the immediate child. So A has 2 children, 2 and 21. So 2 is a small value, 21 is a big value. And therefore, thinking that going down that way is going to, in the short term, maximize the distance, then we go down to 21. But once we go to the 21, then the next one, 21 has 2 children, 7 and 9. So we go down 9 because 9 is the bigger one. Then 9 between 11 and 12 is going to choose 12. So then essentially we have 8, 21, 9 and 12. And this is going to be the path that is discovered by greedy. And in total sum, this will be, okay, this is 30, this is 21, 21, 42, 50, okay? So here, greedy is going to discover 50. Now, can we work out what is the optimal answer here? So what is the optimal answer? So the optimal answer here, if you do go through all the possible leaf nodes, the optimal answer would actually be the leftmost path, right? So 8, 2, 67, 14. So it will be 8, 2, 67, 14. And if you take the sum, this is 10, 77, 91. So indeed 91 is much larger than 50. So why is it that we cannot discover this based on the greedy? So the main problem is that when we go from 8, it's 2 here and 21 here. So then 21 is higher than 2, right? So we don't see what follows after that, right? So that's the point about being greedy. Being greedy means we are being short-sighted. We only look at the next one step. There might be a bigger reward down the line, but we are usually blindsided just based on the thing that are immediately in front of us. And in that case, we are then trapped into making a suboptimal decision. So in this case, the 21 may seem good in the short run, but in the long run, it's just not as good anymore, right? So there are some ways to try to reduce this weakness of greedy. So for example, one possible way to do it is to increase the look ahead. So let's say we are being a little bit more far-sighted. So we can, instead of just looking ahead by 1, so we can look ahead by 2, for example. So in deciding whether we go to 2 and 21, we just don't compare only 2 and 21. We basically ask, well, let me look ahead one more step. If we go to 2, what is going to be the sum I can get to after that? And for 2, the maximum of the children is 57. So in that case, you might then decide to go down this way, because if you look ahead 2 steps, you may actually discover that it has a bigger value. Now, so what it does is that it increases the quality of the greedy answer. But at the same time, it's going to increase the number of steps you need to do. Because if you keep doing this, right, you keep increasing the look ahead, instead of just 1, let me consider 2, let me consider 3. Now at some point, if your look ahead is as far as the height of the tree, essentially now you're really talking about brute force. So in that case, then you may not be able to compute it efficiently. So there is that trade-off between being greedy and being optimal. And essentially you're playing between this trade-off of computation, how fast it is, versus what's going to be the overall quality of the solution. Okay? Now the next part of the question asks whether or not you can recreate another tree that will show a similar phenomenon where you may not be able to get the optimal based on being greedy. This one is very easy to create, right? You just need to make sure that doing something that is suboptimal would actually give you a bigger value or a bigger payoff in the future. So for example, we can create a simple tree here. So let's say it could be that you start from, let's say 2. So then you have 2 branches. You can create one to be a small one, another one to be a big one. But the small one, which is bad in the short run, may eventually maybe create big values down the road, right? So whereas the one that's here, 10, it may sound good in the short run, but in the long run, maybe it just doesn't have as much stuff down the line. So it's not difficult to create such examples where greedy is going to make a mistake. And the mistake that greedy made essentially is to be trapped by a short-term decision that pays off in the short run, but may not pay off in the long run. Right? Any clarification here? I think the point of this question 3 really is about the notion of greedy. When does it fail? And it's going to fail when it prematurely pick what it considers to be the best position, when it may not actually be.